right, everybody, before we move on to volume, I want to just clear up one little point for everybody. Make sure that we know what's going on. So I said lateral faces, for instance, are the ones that are coming up from the base, coming up. So these are lateral, okay? But I want to talk also about height versus slant height, okay? So the height of this pyramid is the total, let me get it out of the glare, the total overall height to the center, the vertex up here, and it's the height that goes through the center of it, and it needs to be perpendicular to the ground, okay? So because this vertex is kind of in the middle, what you can think about is what if I put something right through the center, a vertical, right through the center of my, in this case, pyramid, but it also works for a prism and stuff like that. If I put it right through the center and it went right straight up, perpendicular to the ground, and went straight to the vertex, that's the height, okay? So there's a really great picture. I'll show you it in a second, okay? The other one, the slant height, is let me look at this overall triangle that's coming up here, and let me lay a ruler, for instance, up against it and see how far is it from the base to the vertex in this case. If it was a prism, then we'd say base to base, okay? But how far is that? Well, if it was a prism, it won't have a slant height, right? It'll have just a height, because those are all perpendicular. But this one, you can see, look at that ruler, it's slanting, right? Okay, so that's the idea, that's the difference between them. You know I'm not an artist, so let me pull up a picture out of the book and show it to you. It's on page 463 of your book, if you're looking at that. Oop, give me a good focus. All right, there we go. So if you look at this picture, you can see the height goes right from the center of the pyramid all the way to the vertex, whereas the lateral slant height is on the face of the pyramid, so it's actually sideways. So which of those do you think, just looking at the picture, is shorter? The actual height is shorter, right? Because it's a perpendicular and it goes straight up. But the slant height, you got to go all the way up the edge of that, or the side of that triangle, right? To get to the top, to get to the vertex. So it's a farther distance. So this kind of might lead us into the Pythagorean Theorem and comments about that, because the vertical height there is perpendicular to the ground. You could actually see kind of some right triangle stuff coming out of that. So just a difference, the height perpendicular and the slant height runs along the face of the lateral side there, the lateral face. So there you go, that's the difference. Okay, just to make sure we've got that all straightened out. Okay, so now, this particular document camera just doesn't like to focus very well. All right, now let's talk about volume. So for our purposes, volume in our book that we're using right now is in 10.1, and again, we're talking about volume of a three-dimensional object, right? Okay. So these actually become pretty easy for prisms and can become a little more complicated for pyramids. I don't care that you know exact formulas. That's not what I care about at all, so I'm not stressed out about that. What I want you to know is how volume comes to be. So for instance, the easiest one for us probably is just a prism that's rectangular, right? This has a square base and rectangular sides. So he's a prism. Excuse me. And whenever we look at him, we often say for volume, what we want to know is what would it take to fill up the entire insides of this particular object, right? So people often will say, well, what you can do is you can take cross sections here and cut it in half, or cut a slice, take a section out and look at those. Now, the reason it's easier for prisms is because, especially if they're vertical, we can see it. The oblique ones work the same way, it's just harder to see it. But if I take a cross section from way down here at the bottom of it, or right here in the middle of it, or way up here at the top, what do you think about those? Every cross section that I take, if I could just cut off cut off that top right there and hand you that piece right there at the very top, what would it be? It would be a square, right? And if I pulled a piece, a cross section out of the middle here, just cut it in 2 pieces and pulled out the middle section there, and I looked at it, it would also be a square, right? Okay, same thing off the bottom. Because it's a prism and because the bases are congruent, the cross sections all the way up are the same. So what they tell us in general for a volume of a prism is that what we should do is figure out the area of the base, however big that is, right? And then figure out how many of those would fit in the total height. And again, here I'm looking at perpendicular height, so, and this guy is right, so he's okay. And I'll multiply it. If I knew the area of this base, and it's 1 unit thick, and I know that this thing is, say, 7 units tall, then whatever that area is, there are 7 of them in there, that's how much it would take to fill this object. Okay, so that's kind of what's going on in here, and we can see it. That's pretty easy for us, I think, for whenever it's a square-based prism. Okay, the weirdness, though, happens, what if I had this triangular prism? Well, the process is still the same, right? Take a cross section, take a cross section, take a cross section, take a cross section, cross section, cross section. As many as you can. If I call it 1 unit tall and I figure out how many will fit in there, all I really need to do is figure out how big would it be if I sliced off the base here, right? How much area is in that base. Figure out that cross section. Figure out how many of those cross sections fit in the total height, and you're good. Now the difference here, it's still area of the base times the height, but the difference is in how you find the area of the base, right? In the blue guy, it was just a square, length times width kind of thing, or side squared. And here, whenever I'm dealing with a triangle, I'm going to have to do 1/2 the height times the base of this triangle. So I'm going to have to find the area of this triangle and then multiply it by however many tall that is. Okay. What about for this guy? Remember, he was a square base and he was this tall, right? So I would slice off that base. It's a square. Figure out how big that is, and then figure out how tall it is, so how many would fit in. Okay. And as I get into other more different prisms, this guy's a little bit more different, but he's still a prism. So I think about it, I just need to find the area of that pentagon, because he's a pentagonal prism, right? Find that area of the pentagon, figure, uh-oh, I lost my base here. Figure out how tall is this, so how many would fit in there. There we go. If each pentagon is 1 unit tall, how many will fit in there? And so take the area of that pentagon, multiply it by however many will fit in there. That's your volume. So the difference here whenever I'm looking at a prism is that I'm looking at finding different areas of bases. That's the weirdness that happens here. Okay. Some of the unusual guys that are out there, again, we're not going to worry too much about them, but the cylinder, we looked at him earlier. If I take a cross section off this, again, this isn't a prism or a pyramid technically, but we can approximate it with all these little rectangles, right? If I take enough small rectangles, they'll smooth out and make it more circular. But if I take a cross section on this one, his bases are both circles, right? So if I cross sectioned him, what would I get? A circle, right? So the base, the area of the base here for the cylinder is a circle. So it actually works the same way. Take a cross section, it's a circle, 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 all the way across. How many of those will fit into this object? Okay, so that's area of the base times the height. It's just that now I'm finding the area of a circle instead. Okay, so that's how this becomes a little bit different, a little bit unusual. Your book has some really great, much more greater than mine, pictures for all of these things. So again, take a look. This is actually page 521 Here's a lovely picture where they explain what a vertex and a face and an edge was. I should have used that last time. Here's some, they're calling these hexahedrons. Hexa meaning 6, right? So that's a 6-faced three-dimensional object right there. Here they've got heptahedrons, meaning hepta meaning 7, right? So in this case it's a hexagon for the base and then 6 faces coming up. That's 7 total. In this case it is pentagons for the 2 bases, 2 plus the 5 faces, that's 7. So you can see how they come up with them. So they've got way better pictures than mine would be. Here's a regular dodecahedron, which is like that calendar that I showed you guys the other day. So there's some regular polyhedrons. Over here on page 522, they talk about some, here's one that's an oblique. You can see it's a much better picture than mine was. Here's an oblique triangular prism. So it's slanted, right? It's leaning. The interesting thing about these oblique ones is if you end up needing the height so that you can find the volume, you want the perpendicular height, right? So it's the perpendicular height to the top base there in that case. So they're a little bit different. Here's a great picture of what a lateral face looks like, a lateral edge. Here's my bases. So you can see all of that stuff coming in here. They've got these lovely pictures of hexagons and different kinds of pyramids. Here's one, this is difficult for me to draw, that's why I didn't draw it. Here's one that has a trapezoidal pyramid, okay? What does that mean for me? It means that the base is a trapezoid. So this is what I was talking about in the last video where I said these triangles aren't always going to be the same, right? Because the triangle that matches up to the base of the trapezoid here, the edge here, he has a really short base on this triangle, right? But this one that matches up to the big base of the trapezoid at the back, that's a really big triangle back there in the back. So they're not always going to be nice and pretty and regular and everything. All of the faces match up exactly. So they've got a really great picture of that and why it doesn't work like that. Okay, so there you go. Page 523, some lovely pictures of cones and oblique cones, so you can see how those happen. All right, so we've talked about pyramids or prisms. Now what about pyramids? Okay, the volume of a prism, I think most people have heard of this or seen it before, but the volume of a pyramid, that one's a little bit trickier, okay? And again, I would never expect anybody to memorize formulas for me. I'm not about memorizing, at least not these kinds of formulas. So let's use that same idea that we had for the prisms and talk about it. If I take a cross section here on this pyramid, what's it going to look like? A triangle, right? I hope you're saying that. And as I take cross sections as I come up here, I'm still getting triangles, right? If I cut out a little piece right here and pull that out, it's still going to be triangular because it's still going to have this thing. It's still going to have 3 faces that are defining what's going on in the middle of that thing, right? So I wish I could like slice this up for you. But if I cut out that piece, I'm still going to have a triangle. It would be like I took this guy and instead of this being the base, I cut it right there and that's the base. It's still a triangle, it's just a smaller triangle, right? And here's still a triangle, just a smaller triangle, and so forth, until I get to the vertex, and eventually all I'm going to have is just a point. So I'm just going to have a location in space, no area in there, right? So the problem with this, the reason why it becomes tricky, is that the triangles are getting smaller and smaller and smaller and smaller, right? So let me show you just one thing really fast about these. You can judge for yourself and play with it. So here's the pyramid that was triangular. And what I'm going to do is I'm going to put, oh, it's not going to fit exactly. You'll get the picture, I hope. I'm going to put the, oh man, it'll work better with a cone. Let me do that guy. I'm going to put the pyramid type guy, here the cone's not exactly a pyramid, but you get the point. I'm going to put him inside of the cylinder. So we know how to find the volume of the cylinder. We already figured that out. But when I put the pyramid, the cone in this case, inside of that, what we see is it takes up a certain portion of the overall cylinder. So what we actually end up doing in most cases with a pyramid, or in this case a cone, is we will take the formula for finding a cylinder, okay, well that's the area of the base times the height, okay, and then we'll multiply it by some fraction. And in this case, I believe the fraction, I'm trying to remember, I think it's 1/3, but I'm not sure. But the fraction of the space that it fills up, that's what I'm after. So whenever you see these things, there'll be unusual formulas for finding the area, the volume of a cone, or the volume of a prism, a pyramid, and that kind of thing. And I'm looking for it, and I'm not seeing in your book right off the top of my head. I'm not seeing the formula for the volume of a cone. Of course, I don't see it. Dang it. Okay. You can look it up if you need to. Anyway, I don't really care about the formula, but you can tell it's taking up a portion of it. The fact that they have the same bases means that I can take the original formula and modify it to make just a fraction of it. And a similar thing would happen here with my triangle guys. You can see, there it goes. So there's my triangular prism, right? And then I've put the triangular pyramid inside of it, and you can see it's got the same basic height, the same basic base, but it's just a matter of, because it's slanting in and coming together in one vertex, one point, it's not going to fill up the entire volume of the pyramid. So that's the difference. So the questions in this particular homework set, if you look at them, there's a lot of kind of true, false, and stuff like that. So for instance, one of the true, false questions says, dun, 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 a hexahedron, here we go. A lateral face of a pyramid is always a triangular region. Okay, so here's the pyramid. The lateral face, it starts out as one of the edges of the base and comes up to a vertex up here. So because it's starting out wide and coming up to a point, what do we think? Yeah, it's going to be a triangle. That's the way it works out, right? So it says a lateral face of a pyramid, here's a pyramid, is always a triangular region. That is true. Now, it doesn't have to be the case for just this one. Remember, we looked at other situations. Here was a hexagon and so forth. Hexagonal base, but still has a triangle as one of its lateral faces. So there you go. All right, I think that's most all of it for the volume. I told you it would not be as bad as the surface area. This would be a shorter video. There are a couple of weirdo, you can just read in the book. There are a couple of unusual definitions that they use sometimes in some of the homework, so go back and look for it. There's words like the axis. Generally, that's the axis would be like the perpendicular, basically. So if this is my prism, and I put a straight up and down, a line going through the center of it, it would be the axis. Like it could spin around it, and it would be basically symmetrical around that line is what we're looking at. So they've got some words like that. They use the words right, like a right cylinder versus an oblique cylinder, so right and oblique. They use those a lot. So hopefully that's enough to get you through the homework. If you have any questions, you can email me, and I hope that you have a lovely time working on this homework and the homework for surface area. All right, thank you.